I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic wave equation, uniform plane waves and its applications. And uniform plane waves, it is an electromagnetic wave, originates from a point in free space, spreads out uniformly in all directions, and it forms a spherical wavefront. So, an observer at a large distance from the source is able to observe only a small part of the wave, and the wave appears to him as a plane wave. And for this wave, an electric field E and magnetic field H are perpendicular to each other and also perpendicular to the direction of wave propagation. So, a uniform plane wave is one in which E and H lies in a plane and have the same value everywhere in that plane at any fixed instant. And uniform plane wave traveling in z direction, for example, the space variations of E and H are 0 over z equal to constant plane. So this implies the fields have neither x or y dependence. So we can write the variation in x and y is 0, that is dou by dou x equal to dou by dou y is equal to 0. So a plane wave is transverse in nature, that is electric and magnetic fields are perpendicular to the direction of propagation. So these waves are also called as transverse electromagnetic waves or simply TEM waves. So this is the structure of electromagnetic that is uniform plane wave. So here you can observe the electric and magnetic fields are perpendicular to each other, and it is also called as TEM wave. And by deriving the wave equation, assuming a plane wave is traveling in the direction of x-axis. So the electric field has only the component Ey in y direction and the magnetic field in z direction, that is Hz. So it is said that the wave is polarized in y direction because the electric field direction is y direction. And considering a non-conducting medium like free space, we know that the current density is J is equal to 0. So from Maxwell's equation, from Ampere's law, we can write del cross H is equal to J plus dou D by dou T. Since for non-conducting medium J is equal to 0, the conduction current density, so we can write del cross H is equal to only displacement current density dou D by dou T. And we are expanding this del cross H in rectangular coordinates. We can expand at the left hand side x vector dou H z by dou y minus dou H y by dou z plus y vector dou H x by dou z minus dou H y by dou x plus z vector dou H y by dou x minus dou H x by dou y is equal to dou by dou t of x dx plus y dy plus z dz. So for a uniform plane wave in traveling in x direction have only the component of equation 2 is minus y of dou H y by dou x equal to minus y of dou dy by dou t, because we have the component of y in the component of electric field in y direction and magnetic field is in z direction. So dou H z by dou x is equal to minus epsilon dou E y by dou t. So Maxwell's equation from Faraday's law gives del cross E is equal to minus dou B by dou t. By substituting, we get the right hand side of the previous expression as minus dou by dou t of x bx plus y by plus z bz. And for a plane wave traveling in x direction, the only component of equation 6 can contribute is z vector dou E y by dou x equal to minus z vector of dou H z by dou t. So we can write dou E y by dou x equal to minus mu into dou H z by dou t. So equation 4 relates the space derivative of Hz to the time derivative of Ey, and equation 8 relates the space derivative of Ey to the time derivative of Hz. So by differentiating equation 4 with respect to time t and differentiating 8 with respect to x and Hz can be eliminated and the expression for Ey can be obtained in terms of t and x. So proceeding in the similar way, we can get the equations dou by dou t of dou h y by dou x equal to minus epsilon dou squared Ey by dou t square, and similarly dou squared Ey by dou x squared is equal to minus mu dou by dou x of dou hz by dou t. So dividing by minus u gives minus 1 by mu dou squared Ey by dou x squared is equal to minus dou by dou x of dou hz by dou t. So from this we can finally conclude the expression dou squared Ey by dou t squared is equal to 1 by mu epsilon dou squared Ey by dou x squared. So this is called the wave equation for in terms of Ey, and this is the scalar wave equation in simplest form. And similarly we can get the magnetic field expression dou squared hz by dou t squared is equal to 1 by mu dou squared hz by dou x squared. So this is another equation, wave equation in terms of magnetic field, and these two equations are called wave equations, or sometimes called as D'Alembert's equation. And this 1 by mu epsilon, we know that it is velocity the whole square, that is v square by is equal to 1 by mu epsilon. By substituting, the wave equation becomes dou squared Ey by dou t squared is equal to v squared dou squared Ey by dou x square, and this volts per meter second is equal to v squared volts per meter cube. So the velocity is meters per second, we know it is the unit of velocity unit. And although uniform plane wave is a very idealized case, it can adequately model many practical situations in wireless communication, radars, etc. So for example, fields impinging on receiving antennas that are far away from transmitting antennas are practically uniform plane waves. So now the assessment question: the properties of uniform plane waves, D'Alembert's wave equation, importance of uniform plane waves. Thank you.